All right, how's it going, everybody? We are here on Monday of week 10. We are starting chapter 10 today. We just finished up our chapter 8, which was on applications, advanced applications of integration. We skipped chapter 9 in this textbook because 9 talks about differential equations. By the way, I am teaching the differential equations class next semester. It's Math 55. After you take Calc 2, Math 50B that you're in right now, you take Calc 1, then Calc 2, and after Calc 2, you are then available to take both Calc 3 and differential equations. All right, so DiffEq has a prereq of this class right here. Differential equations is by far my favorite class to teach, period. So much cool stuff happens in there. So I would strongly encourage all of you to come hang out with me again next semester in DiffEq here. But in any event, that's in my opinion, it's a ridiculous topic to smash into one chapter of one class, especially considering the fact that one semester, next semester, isn't even remotely close enough for me to cover all the things of interest associated with even introductory topics with differential equations. I wish I could teach 4 different semesters of differential equations, so to cover it in one chapter is not really a sensible thing to do. It's a huge branch of mathematics, doesn't just get one chapter. So that's not even covered in this class at all. That's its own entire class, Math 55 at College of the Redwoods, and I'll be teaching that next semester, and it's awesome. It's the most epic justification of every single shred of math that you have ever learned. It all comes together in one place in DiffEq, and it is awesome. So come be with me next semester. So this semester, what have we seen? Well, if I'm going to sum up this semester in 2 brief statements, it's integration is really important. It's how we compute like most things of interest. All areas, all volumes, all lengths, all surface areas are all described by integration. And what we need to realize is that those all represent meaningful quantities. We've looked at physics quantities like work. We have looked at probabilities. We've seen lots of other things, even interesting Calc 1, such as things like the integral of a velocity curve gives distance, statements like that. So integration is outrageously important as a computation that we would like to do, but our other statement of the semester is integration is really hard. So what we're kind of learning is that sometimes we can change our perspective and then integration becomes easier. And when I say change our perspective, I mean rather than thinking about X and Y land, maybe we picture U and V land, meaning maybe we perform integration by parts. By changing our perspective, by changing the variables that which we are considering to be the variables of interest, sometimes things become easier for us than they used to be. Right? So we've done several of these. We've changed our perspective into a trig perspective, and that was helpful. We've changed variables. That's a change of perspective. We're going to look at 2 alternate perspectives from which we could be viewing our scenarios rather than a traditional XY rectangular coordinate perspective. And we're going to see that there's some things that are much more easily handled in these alternate perspectives. So this is a huge trade-off. On the one hand, you now have to be able to manage things other than just y equals f of x forms of equations. But on the other hand, the reason that we want to have other scenarios that which we can view these things is because performing our calculus operations is probably going to be easier in those scenarios for some certain cases. It's not like polar is just better than rectangular or something like that. That's not a generally true statement. But for lots of shapes that are circular shaped, polar is probably better to describe them than rectangular coordinates, and therefore our calculus will be easier to perform because our expressions dealing with those quantities are going to be much simpler because we're using a coordinate system that's defined to talk about those types of shapes, right? So this is saying pick the right tool for the job, and sometimes your tool is your perspective here. And so in this chapter, we're going to look at 2 alternate perspectives. One of them are parametric equations. That's today and tomorrow. Next week, we're going to talk about polar coordinates. Fortunately, all of you guys are already comfortable with the basics of polar coordinates. So we'll be able to kind of get into that one a little bit quicker. Parametric curves are not necessarily a thing that it's expected that you've necessarily seen before. So really what's going to happen this week is today I'm just going to talk about parametric equations. There will be no calculus that we do today. Tomorrow, we're going to talk about calculus operations on parametrically defined curves. So today we're kind of introducing the perspective. Tomorrow we're seeing how can we apply calculus operations to that perspective. Same exact thing. Next week we'll talk what's up with polar coordinates, but fortunately we already know what's up with polar coordinates, so we don't have to spend much time introducing them. But then we want to say, what does it look like to do calculus on polar coordinates? And fortunately, most things stay the same. The thing that's going to change is that some computations are going to either become easier or go from impossible to possible because we've changed our perspective. And by the way, I just want to throw out there real quick, I've already showed you kind of one of these this semester that we talked about and I know I've brought this up like a million times by now, but e to the negative x squared we can't do. But then if we extend this to being e to the negative x squared plus y squared, dx dy, then what you'll learn in Calc 3 is that we can rewrite this in the polar form as e to the negative r squared. It turns out that dx dy will be dr d theta, not just a dr d theta. And now we can u sub this guy right here. So this is a perfect example. It just requires a little bit of Calc 3 to get through this example, but this is an excellent example as to how polar coordinates can help us make things go from impossible to possible by changing our perspective to reflect a perspective that's more appropriate for the given scenario. Since e to the negative x squared plus y squared is a symmetric mound, it's got sort of circular cross sections. Circles are involved, polar coordinates are better for the computation. That's the kind of intuition that we're going to try and develop here this week and next week. So, but this is polar. This is me getting a week ahead of myself, and in fact, this is me getting a semester ahead of myself right here because this is a 3D integral right here, but still, hopefully you guys can kind of see that that concept is there, that if we convert to a new measurement system, maybe our computations get a little bit easier. So let's talk parametric curves. So in 10.1, we're going to get comfortable with parametric curves. That's today. 10.2, next video, tomorrow, we'll look at actually applying the calculus to these. So today is a no calculus day. We'll see if that means this video is any shorter or not. So what's a parametric curve? Instead of directly defining a relationship between x and y, meaning we're no longer in a scenario where we need to be able to write expressions as y equals f of x or x equals f of y, we're instead going to allow x and y to be functions of other parameters, or more simply, just one other underlying parameter that's actually controlling both our x and our y values. So when you see parametric curves, what you should be thinking is that they are curves that are defined not by x and y values, but defined by parameters that themselves define the x and y values. Right? When I think of parametric graphs, I think of the trajectory of a fly. There is one graph that's in my head always when I am thinking of generic parametric curves, and that is a fly's trajectory. So it might be that a fly starts at a given location, and maybe it then flies around the room in some strange pattern. And maybe it then comes and it lands on my face for the 46th time this afternoon, and I freak out, right? So what you should notice here is a couple things. One, parametric curves can have starting and ending points right here. Two, parametric curves don't have to be functions. Notice that this not only fails the vertical line test outrageously. I'm noticing that like right here, this vertical line has 1, 2, 3, 4, 5 different intersections for a vertical line. Vertical line test is not going to really be a relevant feature for us here today. We aren't going to care if these things pass the vertical line test or not. The other thing that's extremely interesting is this function crossed over itself right here. Now, so far, I've done a bad job describing this as a parametric curve, and here's the reason why. What we know based on what I verbalized right here is that this is really where the fly started. So I might refer to this as my location time 0, t sub 0, to say that's my initial time. And then maybe I would describe this over here as my t sub f. My time final is occurring over here. It's supposed to be an f right there. And we're still looking at x and y axes. But notice that I'm not describing the locations of interest based on x or y locations. I'm so far describing them based on times at which we have been at those locations. The other thing that's interesting here is that we technically have a point of intersection of our curve right here, right? Our curve is over top of itself, but is that necessarily truly a place where the fly was in the Like what's really the same? Is the fly's features identical at this point in time or not? And the answer is, well, it depends on what variables we're discussing here. But what you should notice is that in a sense, there's like a direction associated with this curve, right? The fly was moving in a direction here. It was moving along the curve from the time zero to time final location, right? So another important thing about parametric curves is that they're directional. They're not just a curve in space. They're a curve that goes from one point to another point. You should notice that the arrows are always going to be pointing in the direction that is associated with an increase in time or an increase in the parameter. Very commonly, by far the most common parameter to use in parametric equations is t, and that is because we often think about these in physics senses where the t is referencing time. So it's not always the case that t is time, but you should always use t for your parameters, and you should always think of t as time. Think of this as like a movie being played out rather than an object that exists. All right? You should really be picturing this as a dot that is moving following this curve rather than thinking of the curve itself as being the object of interest. We are following a point in space as it moves throughout space. So the other interesting thing about this intersection right here is that when we think x and y, we would think that this point is exactly the same no matter how we hit it, right? If you go through the xy point of 4 or 3, 4, or whatever this point is right here, then we went through 3, 4 twice. But the difference in our context now is that we were once at the location in 3, 4 at maybe what we'd call time 1, but then maybe it took us another 4 seconds to get back here. And so now we're at that point 3, 4 again at time 5. So notice that there's a slight distinction that I could distinguish between the 2 points that both exist at xy equals 3, 4, because one of them has a small time because it's at the beginning of our path. Another one of them has a much later time associated with it. So I can actually distinguish not just between these 5 different locations on this vertical line right here, because they all are associated with different times and different y values, but I can also even distinguish between individual points that might overlap on our curves because they should be occurring at different times in our trajectory's path. So a very common thing to do when we're thinking about parametric curves is to either think about like the trajectory of a fly or something like that, or to just say a particle in space. A lot of parametric stuff that you'll see is a particle follows the path defined by blah, 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 blah. And it's really just us trying to emphasize the fact that the object of interest here is not the whole curve. The curve is the underlying path. The object of interest is really just sort of like a point. It starts right here, and that point moves with direction along this given path out here, right? So this is sort of breaking our minds from the idea that when I say graph y equals x squared, you think of the object as the parabola. Now instead, when we parametrically define something that will have the shape of a parabola, I don't think of the object so much as the curve, as the object being maybe the particle that traverses the curve itself out there, right? So, and that's a bit of like a subtle difference right there. And that's maybe a little bit more for me to like help my mental image of what's happening right here. But it's good for us to kind of break away from our traditional concept of how we define curves in space, and especially wanting them to be functions all the time. Not only can we fail the vertical line test, but we can even cross over ourselves, and that shouldn't be a problem with our parametrically defined functions. So what we see here is this key features is failure to pass the vertical line test is not an issue. There's no ambiguity here because I have time to help me distinguish between these cases aside from just x and y. I'm not plugging in x to get y. I'm plugging in t to get x and y. And that's why our vertical line test doesn't matter here. The second thing that's really important as a key feature for parametric curves is that the curve has a direction. It's not just an object, it is an object with direction. All good parametric curves have arrows on them indicating the direction of motion that's associated with an increase in t or an increase in whatever your parameter of interest is. It might not be the letter t, obviously, but I'm going to use a bunch of t and we're going to think about it as time. That's just the most helpful thing for us to do here. So what we're going to do is we're just going to look at a smattering of examples here. Some of these are like, a bunch of these are like super basic, super classic examples, but it's worth it for us to talk through them to kind of see some of the changes that we can impart on these graphs right here. So let's look at a couple. The book does a couple of these. I threw in a couple of these. And we just want to see how are things the same, how are things different when we define parametric curves out here. So here's our first 2 easy examples, and you should first look at these and say, those look really similar. You should immediately identify what's on the screen right now, what's different between example 1 and example 2 right here. And so I want to go ahead and start graphing a parametric curve. So I'm noticing here that x is defined based on the parameter t, y is defined based on the parameter t, and we are given the interval of times over which we should be considering this curve right here. So the first thing that I kind of like to do is I like to ask myself, is it possible that I could define this thing not parametrically? Can I get back into my comfort zone of defining y based on x or x based on y here? And what I'm seeing here is this is the simplest possible parameterization of anything ever. X is the same thing as t. I didn't even change variables. I'm literally just calling x a different variable and moving on right here. So this is, in a sense, a meaningless parameterization because I didn't really change anything. X is just t. So we're just using t. So x is t squared is the same thing, or sorry, y is t squared is literally just the same thing as me saying y is x squared. And so we are going to get the parabola here, y equals x squared. Now, what I want to do is I want to make sure I just almost did a very bad thing right there. I put an arrow on the top of my curve, but I am no longer using arrows to indicate end behavior here. What's important for me is that while I'm still in the XY plane, I want to draw arrows on my parabola that indicate the trajectory that we're following here. So I'm noticing that as t gets bigger and bigger, and by the way, t certainly goes from negative to positive infinity here. I typically find it useful to like pick an arbitrary starting point to like think about things from. So if I think of like t equals 0, t equals 0 is associated with the point xy equals 0, 0. So I could do some things on here like label t equals 0 on this point. I can identify that at t equals 1, that we're getting the xy point of 1, 1. And so I might identify this point here as t equals 1, stuff like that. Pretty typical to label points on a parametric curve as what the parameter value was that gave you that point. Here, it's what times we're at. You should notice over here that this would be our t equals -1 point. If you plug in -1 for t, you're going to get -1 for x, but still +1 for t squared. And oops, I just realized I wrote that wrong. Very important, as t equals -1. So what you should see here is that as our t values increase, we seem to be moving from left to right along this our parabola here. So it will be appropriate for me to put the arrows indicating that direction of motion. This particle is moving along a parabolic path, starting from the far left, moving to the far right as that plus and minus infinity goes right there. So for our second curve, what's changed here? I'm going to draw a bigger picture because that last picture was unnecessarily small. So what I'm seeing here is we still clearly have a parabolic relationship here. It's still clearly the case that if you take x and square it, that's -t squared, you're getting t squared, which is y. So it looks like we do have y equals x squared as the curve. So my question is, did anything change because we have a negative in our parameterization now? Oh man, I did that bad thing again here. Not drawing arrows on those things. Arrows are not for end behavior on parametric curves. Arrows are indicating the direction of increase of parameter. You should now notice that if I pick the value t equals 1, that's going to be associated with the xy pairing of -1, 1. This is now my t equals 1 location. And you should notice over here, or maybe I should just say t equals 0 is going to be my 0, 0 location. And that's going to be my t equals 0 still right here. So notice that in this case, as t increases, we're actually moving from right to left. So the shape of the curve was unaffected by the introduction of this negative, but the direction of motion was changed by the introduction of that negative right there. So since a parametric curve has to include arrows indicating the direction of increase of t, these two parametric curves are different. The shape of the curve is the same. The direction that we traverse it is different out there. And that's because we picked up this negative on the t right there. Example number 3. So we're still hanging out in our negative t squared ordering right here. And by the way, because we're going to have Desmos start looking at some of these things for us here, it's very typical for us to, instead of thinking about our xy ordered pairs, to reference our parameterization in this format here. So another way to write this parameterization would be like this. You might see something give you this ordered pair. Say, the parameterization for xy is given by negative t squared. That just means that x is negative t and y is t squared right here. So and this is how Desmos is going to want this from us, by the way. You should notice that the big thing that changed here is that we are now given these final bounds right here. So here's what I'm going to do. I'm going to think to myself, I know that this is going to follow that parabola really just from the previous examples, right? So redoing my previous work or reusing my previous work, I know that I'm going to get a y equals x squared parabola associated with this guy here. But I maybe don't want to go ahead and plot the entire thing. Maybe I'm going to back up here a little bit. Maybe I should go ahead and find my endpoint locations here. If t is at negative 2, then that's going to tell me that our xy location is at positive 2. I'm using this ordered pair, by the way, here. Positive 2, 4. And if t is at 1, then I know that I'm looking at negative 1, 1. So maybe now I can come over here and try and graph my curve over here. I know that I want to start my motion at the points 2, 4. And I want to end this trajectory at 1, 1. Oh, sorry, negative 1, 1 right here. I know that the shape of our trajectory overall is y equals x squared, so I can draw that shape in here. But notice I'm only performing this motion from time negative 1 to time 2. Okay, I did an okay job right there. Let me just give it a new point. I'm going to just erase the old one here. Not the worst parabola I've ever drawn with a stylus. So in this case right here, we only got some subset of this parabola right here. And very importantly, this is our time equals negative 2. This is our time equals 1. And therefore, this very importantly gets the arrow indicating that we're really starting at the location 2, 4, and we're ending at the location negative 1, 1. So again, that arrow really matters. And anytime you mark a point on a parametric curve, rather than labeling the xy coordinate of the point, it's a little bit more typical to label the parameter value that gave you that xy value right there. What times were we observing when we were at those 2 points right there? So in this case, our parameterization did not change, but the bounds of our parameter did change. This is sort of like a domain, but I'm weary of using the word domain because when we're graphing XY stuff, I know that people still think of domain as our left-Y interval, and that might not necessarily match our T interval of interest right here. All right, so, but it is still the case that the T values that are acceptable were from negative 2 to 1 right there. So now let's look at our slightly more interesting ones, I think, some of our trig expressions right here. In our trig parameterizations, we're looking at this first one here because this is an incredibly common first parameterization here, one that shows up more than almost any other, or at least in my experience working with parameterizations. It's super often for us to want to rephrase trig stuff with parameterizations here. So what I'm kind of thinking to myself again is I want to know some relation between x and y that could maybe help me graph this. So let me just say here, any known relationship between x and y, also known as sine and cosine? Do you know any special relationship between sine and cosine? Is there an equation that you can create that involves sines and cosines? I think that there is. I think that I could write an equation that looks like sine squared of t plus cosine squared of t equals 1. I know that my Pythagorean identity right there is going to help me out with this guy. And notice that in this case, that's just x squared plus y squared equals 1. Oops. So a very common parameterization for what we know as a circle is to parameterize a circle. Rather than giving your equation as x squared plus y squared equals 1, is to instead give the parameterized form of a circle, where x is sine and y is cosine right here. So in this case now my question to you is still this. I know that the shape of my curve is a circle, but what we have learned is that that is not the only thing of interest associated with a parametric set of equations here. In a parametric set of equations, I also want to know in what direction is our motion. And I'm also noticing that since we have finite bounds here, we aren't going from negative to positive infinity, it seems like we should have a starting and ending location. So I want to ask myself, before we sort of move on with this example here and go on to the next one, maybe I should just do this, is I'm going to say to myself, at t equals 0, what are we looking at? We're looking at sine of 0, cosine of 0, and that's going to be 0, 1. So it looks like our starting location is right here. The next question I want to ask is, in what direction do we move? What direction of motion do we experience? So here's the thing I'm thinking. We started at t equals 0, and I just want to wobble t a little bit. If you make t some tiny angle, tiny positive angle, right now t is like our angle in here. We think of it as time, but it's an entry into sine and cosine, so I'm thinking of it as an angle. So think of t just being like 1 degree, right? If that's the case, then what happens to sine? What happens to cosine? Well, the sine of 0 is 0. The sine of 1 degree, it's about, sine of, okay, I was about to say an approximation statement associated with radians. In any event, we should get a small positive value here. And so notice that this is in our x-coordinate. Well, let me just do this right here. I'm just going to say let t be some small positive number. Then we should be getting the sine of t, the cosine of t. If t is a small positive number, then sine of t is a small positive number, and cosine of t is a large positive number. So that's just indicating to me that this should be our next point of interest that's on our graph right there. We're clearly getting two positive numbers, so we're going to be in the first quadrant. So all this is telling me is that it looks like our direction of motion on this graph is going to be clockwise. So notice one thing I could say to you, think about some questions I might ask. If I give you this parameterization, a question I might ask is, what is the initial location and what is the direction of motion? You would tell me the initial location is 0, 1, and the direction of motion is clockwise. We could describe some things that are not explicitly stated about this parameterization by stopping and investigating a few values that are right here. Right? Now, another thing that you should notice here is this. This equation for a circle is really actually symmetric. If I swapped x and y, I'm still getting the exact same relationship. You should notice here, in fact, I'm hopeful for next week that you guys are all a little uncomfortable with this parameterization right here. Why? Well, we typically denote x to be with cosine, right? X equals r cos theta, y equals r sine theta. That's something that should be tattooed on your forehead if you've forgotten it from trig. So go get your forehead tattoos if you need it between now and next week. X is usually associated with cosine, and y is usually associated with sine. So you should notice here our circle shape would still be the same if we swap these parameterizations, but it might be the case that we either start in a different location or travel in a different direction if we were to change up our parameterization. So this is sort of leading you to believe there are lots of parameterizations of a circle, and they change depending on where we would like to start and in what direction we would like to travel, since parameterizations are more about trajectories than the curve itself being the object. All right, but we'll come back to seeing that in a second here. So let's look and see how another thing could be changing in here. So let's keep number 4 up on the screen and see what we are interested in for number 5. At number 4, we had x being sine, and number 5, x is still sine, but it's of 3t. Y, same change. Interval, no change right here. So the only thing that's changed is we now have an argument of 3 inside, also associated with the t. So what's going to be the difference between these two here? Well, actually, I think what I should do is I should indicate one final location over here. We know, certainly, very basic trig facts right here. If this is the location of t equals 0, then this is also the location at 2 pi, right? 2 pi is how long it takes us to experience one full lap around a circle. So something else is going on over here, right? Now, I'm thinking to myself, it's still the case that sine squared of 3t plus cosine squared of 3t equals 1. That is x squared plus y squared equals 1. Still a circle of radius 1. Oop, r equals 0. But what's changed in here now that it says 3t? Well, now the thing that I'm picturing for myself is that even though our t values are still just going to go from 0 to 2 pi, my new question is, what are the arguments that are going inside of sine and cosine? And when I say the argument of sine is not t. T is our variable of interest. The argument of sine is 3t. So it looks like the things that are going to go into sine now is, maybe I'll make this statement right here. I should have given myself a smidge. Oh wait, can I do this? Let me be smart right here. Oh yeah, look. Oh man, I thought I was smart, but we hit the bottom of the page. So I'm noticing here, I could multiply this whole inequality by 3, and I'm going to get 0 is less than or equal to 3t is less than or equal to 6 pi. So what that says to me is this is sort of like us doing exactly the same as the previous example, except that our interval now goes from 0 to 6 pi instead of 0 to 2 pi. So what's going to be the difference? Well, before we took one lap around the circle, right? Our trajectory said start at the top of the circle, go around it once, end at the top. You're done. You hit time 2 pi. There's no more traveling to do. This is exactly one lap. Right? That's what we did. Exactly one clockwise lap right there. It looks like in this one now, we're really going to have our arguments in sine and cosine traverse all the values from 0 to 6 pi, which you should recognize as being 3 periods of sine and cosine, not 1 period of sine and cosine. So it's still going to be the case that we're going to get a circle. It's still going to be the case that if you plug in t equals 0, our initial time, you're going to get 0, 1 for our starting location. But it's also the case that there's several times now that we will take that lap around. And again, I'm just kind of copying my answer from before to put my arrows on this thing right there and to give my initial location. But I'm also kind of noticing now, so what's my next time that I'm going to be back to here? Before it was 2 pi, but now I'm going to get 3 times that for me. So maybe 2 pi thirds and 4 pi thirds and and 2 pi. Sorry, I was right, and I like talked myself out of it. All of those times are associated with this curve right there. This is really take 3 laps around the unit circle. Another way that I like to interpret this is like this. Notice how our time interval didn't change from 4 to 5. We're on example 5 right now. But we went 3 times further. And so, if you went 3 times further in the same amount of time, then your speed must have been 3 times faster, right? So what we're kind of saying here is that this parameterization does give the exact same trajectories, but it will follow them out. It will pass through them all at 3 times the speed as we would have seen this guy right here. So I think now is an appropriate time for me to pop over into Desmos and let's compare example 4 to example 5. And what we're going to do is we're going to draw the curve. We're going to put down each of these two dots on the parametric curve, and then we're going to slide a slider bar for t, and we're going to watch one of these dots move. This dot will move 3 times faster than this one. Both of them will eventually end, though, back at the top again. So let's see if we can pop over into Desmos and make this guy happen over here. Is it happy with me? Okay, I think it's happy with me. Let me just move this over so we can see it here. So I do want you guys to be good with, oh, I've still got my wrong text stuff up right here. I can fix this. Let me fix my view real quick here so I don't have incorrect things on my screen. There we go. Now I'll make myself nice and big so you guys can appreciate seeing my face right here. Okay. So here we are in Desmos. And so I want to teach you guys how to do this. This is one of those things where, like, I don't know, maybe if you're good with your graphing calculator, use your graphing calculator instead of Desmos for most things. Use Desmos for parametric equations. It is better. There is nothing that I'm aware of that is free and easy that is as good as parametric equations as Desmos is. So the other thing is that I'm going to show you how to draw the curve, but what's way more valuable to us is to see the point move along the curve. And this is where things get a little tricky, sort of. So to draw just the curve, you need to give Desmos an XY ordered pair in terms of t. So I'm going to say here, I'm going to even give myself some expressions here. To graph a parametric x of t, y of t curve, give the ordered pair. All right. So I'm going to do exactly this. I'm going to give an x of t, y of t ordered pair. So we just defined this to be sine of t, cos of t. That was our number 4 example right there. And what you can see is it immediately busted out one part of what looks like a circle. Notice that it initially gives us our bounds for t from 0 to 1. At time 0, we're right up at the top like we knew we were, and it looks like this amount of angle that's being swept out right here must be exactly 1 radian. We went from 0 radians to 1 radian. That's the amount of arc swept out by 1 radian. If I wanted to change this, for example, to 2 pi, then I could now see the entirety of the circle there, right? So we have now given it the t bounds from 0 to 2 pi. So this has given us the shape of the curve. But super duper importantly, a parametric curve is not just the shape of the object. It includes starting and ending locations, and it includes arrows of motion. We're not going to be able to get arrows on here, but we're going to be able to get points that move, and that's going to be super important for us. So here's the thing that you need to understand. Desmos knows x and y as variables, and it will treat them differently than if you try to do like p equals something. And let me just show you a quick example. Y equals 2x. If I do that, it immediately gives me a line. But if I say like p equals 2r, it's like, what the hell are you talking? Oh, wait, did it just really do that right there? Oh my gosh. Okay, that's actually kind of annoying right there. Okay, well, okay, there we go. Apparently it's going to be interpreting things as y equals something, a function of x right there, always, regardless of what we use. Okay, I'm making myself a liar right away here. The important thing, though, is that it is understanding that t is a parameterizing variable right there. So what I want to be able to do is I want to not give an entire interval of values for t. I want to pick like one t number, so that I can see where that dot would be on this curve, right? So what I'm going to do is I'm then going to, and I do this for every parametric curve, is give the exact same expression, but to use a generic letter like a. And here's why. Here's the improvement that we get. When we gave this parametric equation in terms of t, it understood that t was going to be a variable that we wanted to graph an entire interval of values of t. It understands this parameterization idea. But what I am interested in is truly just graphing a point. And to graph just a point in Desmos, you just graph a point. You just give it an XY pair. And that's exactly what I did. But here I want to add a slider for A so that it's interpreting A as being a single point of interest. All right? So here's where we're getting into our same scenario here as what we just saw over in Word. I want to let my A values go from 0 to 2 pi. And I want this A value, well, let me just hit enter right here. And notice that I can start my A value at 0. I can see that it's this green dot at the top right here. Maybe I should make this like a red dot so this is more visible. There we go, slightly more visible red dot. If anybody, by the way, has it, I don't know, we're going to see a bunch of graphs this semester, and also, by the way, next semester. If you're taking calculus this semester, next semester, you're going to see so many graphs that if you maybe have some color blindness issues, those would be worth pointing out because sometimes I pick colors that are easy for me to see because I am not colorblind. But I know that a huge chunk of the population is. So if you ever have issues seeing some of the things that I'm graphing, you should let me know. 50C with Steve Jackson next semester. He's going to be graphing things literally every day of the whole course. You should talk to him about colors that are easier and harder for him to see or for you to see. Same thing if you're taking Diffie-Q with me next semester. Let me know if you ever have any color issues out here. All right, I'm thinking that red is a little easier for me to see right here. And so anyway, the point is that we can now see as our A value increases and where we're thinking of A is really being T right here, we can see this direction of motion and we can watch our point be parametrically moved around our curve. And we can see here it clearly does land. It ends right at that final ending point that we know that it should at 2 pi right there. So here's the more interesting thing that we want to do now. Let's now take a competing point out there. Let's first verify that sine of 3t, cosine of 3t is exactly the same. And I'm going to change the coloring of my curve here to be blue so that we can verify that it's the same. And, oh, that's really weird. It laid the blue over the top of it right there. I do want my interval to go from 0 to 2 pi. But what I can do to verify that these are the same is I can just turn off the blue and turn on the blue. And hopefully, again, depending on if you can see my colors here, you can see this curve changing from blue to black. And it's really just because the blue one is overlaying on top of the black one that's right there. So one, I'm convinced that sine of t cos t and sine of 3t cos of 3t produce the same shape of parametric curve, but our trajectories are going to be produced at different speeds because we have these coefficients inside of here. So now let's produce another dot at the location associated with this, sine of 3b. Oh no, I want to make this a because I want a to be exactly controlled by the same exact thing. So cos of 3a. And very importantly, I need to change some colors here again. All right, now what are my smartest two colors here? I'm going to change this to orange and to blue. And change this guy to green right here. So now what we should see, all right, so I've changed some color things up right here. Our original curve and point is black and blue. Our 3 times faster is the green and the orange. And now what happens when I change my A values? Watch now, the orange one is always 3 times further along on the curve than the blue one. And so you should notice that the orange curve, the orange dot has completed its first lap in the amount of time that it took the blue dot to complete a third of a lap. We're going to keep on going. Orange is actually passing down here because at exactly halfway around, they should be matching. And that kind of makes sense to me right there because at 1.5 laps for one of them, we've done a half lap for the other. 1.5 laps is 3 times as much as half a lap right there. It looks like orange is going to complete its second lap at this point in time. Blue has completed 2/3 of a lap. And then finally getting all the rest of the way back around, we can see the blue and the orange come together right up here at the top. They came together at the top right there. And so again, seeing this motion is what's really important right here. So while I can't get the arrows on my curve, I can still clearly see my directions of motion that are associated with my points by putting these sliders with some points out on the graph right here. So again, my process for graphing parametric curves is to graph the curve, graph it in terms of t as an ordered pair, and give the interval of t values of interest. To then place a point on the curve, give a parameter other than t inside of the same ordered pair, and it should instead give you the option to include a slider bar, and now you can slide that slider bar across those same values right there to see points move on your curve from beginning and ending values of interest that are out there. So this setup right here, really, really important that you can do this setup so that you can investigate some of these functions right here. All right, so I'm going to pop back over to our Word document right here. All right. So, okay, come backward. You took a little break there. I know. Here we go. Here we go. So, let's look at another example here, and then we'll do kind of a more difficult example right here. Investigate the curve parametrically defined by these two equations. So what I want to do here is I want to sort of do this a little bit by hand, and then we'll go over into Desmos and confirm our answers. You should basically always, 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 always let Desmos do a whole lot of things for you when you're doing parametric equations, always. Trust Desmos to make a good graph for you. Parametric equations are not anybody's natural instinct. Make sure that technology is verifying stuff for you. On the other hand, what we always talk about is you should always be making guesses as to what you're going to see to the best of your ability, so that when you do see technology produce those results, you can either say to yourself, good, I was talking about what I thought I was talking about, or you can say, apparently I need to change the way that I think about some things here. So here we've got sine of t and sine squared of t. And importantly, both of these are sine. They're not necessarily cosine right here. All right. So here's some statements I think that I can make. Statement number one. I always want to ask myself, is there some relation? Is there a known relationship between x and y? Is there an easy to state relationship? And yeah, x and y are really closely associated. In fact, what does it look like you should do to x to get y? Well, it looks like if we squared x, you'd have y. Right? Y equals sine squared of t equals sine of t squared equals x squared. It looks like we just get y equals x squared. And so the shape is a parabola. What else do I know about this thing? Well, some other things I always like to think about here is what is the range of each of our parametric equations? Really importantly, notice that we weren't given no t information here, right? I wasn't given a bound on t, so I guess I'm just assuming all values of t are acceptable to think about here. So x of t is sine of t, and I know that sine of t is always going to give me values that go from -1 to 1. That's my x span. This is sort of like my domain. And notice here, really importantly, I refer to this as range because the range is the output of a function, and the output from x is -1 to 1. So in one sense, this is the range in the parametric sense. However, this is the domain in the rectangular sense, since the domain describes the span of x values, and that's what I just described. So that's why I said to you I'm weary about using the words domain and range here, since literally it could be one or the other, depending on if you're talking about the parametric version or the rectangular xy version. So be careful with that right here. On the other hand, over here, we've got that y of t is sine squared of t. And so that says we're going to get all the things that we would get from sine, which is -1 to 1. But we know that when we square things, we always get positives. So it looks like this is really just going to be 0 to 1. And it's like this is like our range. So here's some things I'm picturing for myself. I know the shape. I know the x values of interest. I know the y values of interest. So I'm picturing that we should be getting something that's going to look like a parabola. I'm picturing that our x values of interest are going to go from -1 to 1. I'm picturing that our y values of interest are going to go from 0 to 1. And that's how I knew to draw it where I did, right there, right? So the interesting thing here is that this is a finite graph, right? The graph does not go on forever, but our t values do. So I'm not done though, right? I know what the shape of my graph looks like, but I still don't really know what the trajectories actually look like here, right? So one thing I might also do is I might say to myself, what happens when I plug in t equals 0? You should notice here that at t equals 0, both x and y are both 0 here. Um, So what's this going to look like when I try and actually graph this guy here? So this is certainly my t equals 0 location is at 0, 0. And I'm thinking of just like what are some other special values that happen associated with the sine function? When does sine reach its maximum? I'm picturing on my unit circle that sine, the height on the unit circle, is at its max at pi halves. If I were to use t equals pi halves, then you should notice that I'd be right here. That would be at the location 1, 1. And so like on the one hand, it seems like our point just came up here, right? But what happens as t goes past pi halves? Well, as we get past pi halves, our height on the unit circle is going to go back down again, right? So it looks like these values should be decreasing back along the same trajectories that they were. Eventually, our heights on our unit circle will become negative. And notice that height on the unit circle is sine, and sine is describing the x values in our graph. So when I'm thinking the bottom half of the unit circle, in this graph, that's representative of the left half of the parabola. I should say left half based on my hands right there. So it looks like we're going to start at the bottom. We're going to walk up to the top. We're going to come back down to the bottom. We're down here at pi, by the way. And then we're going to come back all the way up over to here. And this will be our 3 pi halves location. And what happens after 3 pi halves? Well, now our values stop being so extremely negative and they start to come back on again. So it looks like what we're going to get is a rocking back and forth motion right here. So notice what my dilemma is with this graph is tough for me to draw arrows. Since the trajectory overlaps itself. How many times? An infinite number of times. Oh, come on. That's not the stuff I was just writing. How could you erase that over there? That doesn't even make sense. Clearly talking about the stuff I'm in the middle of writing right now. What's wrong with you? The undo button. It's not an erase button. Undo the most recent action. It's what undo means. Okay. All right. So it's a little tough for me to draw trajectories on this thing, but I think I can at least describe the curve as starts at vertex, moves to upper right, and to upper left. Back to vertex. Repeat. So in this case, I have an unfortunate circumstance that I don't really have a clear way to describe this because literally exactly half of the time that a particle is sitting right here, half of the time it's moving this direction, half the time it's moving this direction. And so I don't want to put any arrows on this guy necessarily. I've identified some points of interest. And to be honest, I think that you can kind of actually interpret this guy pretty dang well right here. If I were to like kind of continue some labels right here, right? Like a 5 pi halves and a, right? So we're going to go to 0, 1 pi half, pi, 3 pi halves, 2 pi, 5 pi halves, 3 pi, right? And we're going to keep on doing this bouncing back and forth out there. Let's go pop over to Desmos and see if we're going to get that exact same thing over here. So back over in Desmos, I'm going to get rid of my old equations here. So now we are, let me just get rid of all these guys. We are now looking at sine of t and sine squared of t. Notice immediately it gives us exactly this. By the way, I might take this broader. I can't give it, I don't think I can do infinities here. I typically just do things like negative 10 pi to positive 10 pi. I don't know, that gives me a pretty good span so I can see it here. Again, I'm also going to give myself a point that I can move around here so I can see where it's actually located at an individual point in time. I'm going to add my slider. I'm going to do the same thing. If you click on the slider box, then it lets you change these. So I'll do the negative 10 pi to 10 pi again right here and hit enter. And now I'm going to start over here at negative 10 pi. Ooh, and I think I did a thing I didn't. Oh, no, that's okay. So I think that was okay. Actually, maybe I could just press play. Is that too fast? That's too fast. Let's just change this to like negative 4 pi and 4 pi, so it's a little bit smoother of an animation here. And you can see that this particle is just swinging back and forth exactly like we said. Now, notice a slightly dangerous thing about clicking the play button. Right now, it's playing time backwards. Now it's playing time forwards. So you should realize that there's also this kind of reference in parametric curves that we refer to forwards time and backwards time. Forwards time is what the direction of motion is as t increases. Right now you can see this dot is moving left, this guy right here. So as it moves to the right, time is increasing. So this is our forwards time path. Now time is decreasing. So this is like our backwards time trajectory. If you were to go backwards in time, that's the path that things would follow right there. So again, using Desmos to help you see these is a really, really valuable thing to do. So even if you have other ways that you like to graph things, I have a really hard time believing that they're better than what Desmos is providing for us right here. So get comfortable with both of these two setups that you see right here. These will make all of your parametric investigation quite a bit better. So let's pop back over into Word and let's look at some slightly two more interesting questions right here, and then we'll call it a day since we're really obviously more interested in doing calculus here. There's no calculus happening today. So I'm going to tell you what I want here, and let's think about what our parametric equations must look like. I would like to determine the parametric equations that describe the path of a particle. It's going to travel along a circle. So right away, you should be thinking to yourself, one of our terms is sine, and one of our terms is cosine. What do we know? The circle is radius 2. Well, where does radius term go with our sines and cosines? Now, I'm leaving off many things. I'm not putting an x or y here. I'm not putting an argument here. I'm just trying to say, how do we incorporate this piece of radius 2 information? You know where this 2 piece of information belongs. X equals r cos theta, y equals r sine theta. The radius is always going to be our coefficient on the sine and cosine terms, right? So I know that's where my radius piece of information is going to go. I know that I want to go in the clockwise direction. I want to travel around in that clockwise direction. I want to do 2 laps. I want to do that in 1 second. And I want to start at 2, 0. Ooh, so that's 4 pieces of information that we just accumulated right there. We need to really break this guy down. So let's kind of like think about some setups that we could do right here. So let's make like a guess, I guess, is the thing I'm thinking. If we did x of t as 2 cosine t and y of t as 2 sine of t, what is that going to do for us? Well, I'm thinking at t equals 0, our location, t equals 0 is going to give us 2, 0, because I'm going to get a cosine of 0 is 1 times 2 is 2. Sine of 0 is 0 times 2 is going to be 0. So I'm noticing that this one does have the good starting location right here. I know that this is going to parameterize to a circle of radius 2 because sine squared plus cosine squared is going to be equal to a constant. But what's not clear to me, so this is starting at 2, 0, are we going to travel in the correct direction right here? So let's see here. Are we going to travel in the correct direction? I want to travel in the clockwise direction, right? So I'm noticing here, if you make t a little bit bigger than 0 and a little bit bigger than 0, then we would end up in the first quadrant. And if we end up in the first quadrant next, then you should notice that that means that we are traveling counterclockwise. That's no good. We said that we wanted to travel clockwise. All right. So by doing a little bit of an investigation here, by recognizing that if I plugged in a small positive number for t, I get positives for both sine and cosine. Positive, positive quadrant is the first quadrant. That indicates that from time 0, we moved into the first quadrant. So that must be our counterclockwise direction of motion. We wanted clockwise direction of motion. So what's the thing that we can do to fix this? Well, the thing I guess that I'm picturing to myself is I want my heights to not be positive first. I want my heights to be negative first. So by switching, so notice, by the way, before we were doing x was sine, all right, before we were looking at x being sine and y being cosine. In that case, we were traveling clockwise like we wanted, but we had the starting location not where we wanted at the top, according to our current example. Our current example, we switched to cosine and sine so that we could start at the right-hand side over here, but we've lost our clockwise motion. So how can I now fix that? Well, I'm just thinking I would really like my y values to start out heading in the negative direction rather than my y values to head off in the positive direction. So maybe let's just stick a negative on the y value stuff right there. So now, new guess. X of t is 2 cos t, and y of t is negative 2 sine t. Well, now in this case, we're still going to get that at t equals 0, we get 2, 0, so that's good. So we're still starting right there, but now you should notice that if t is a small positive number, then now we're actually getting a positive number for x, but a negative number for y. This is Q4, fourth quadrant, and that says we are going clockwise. So we are moving in that direction right there is kind of what we just showed by, I'm literally not even plugging in a number. I just know you plug in a small positive number into sine and cosine to get positive stuff. Since I have a negative on the y term, we got a negative thing instead right there. So it looks to me like I'm on the right track so far. I've got the 2's handling my radius. Cosine and sine are appropriately oriented to give me my right starting location at 2, 0. Notice in our early examples we had initial locations at the top of the circle instead, but by switching cosine and sine we went from 1, 0 to 0, 1 for our initial location. This ruined our direction of motion by picking these the correct way right here for our initial location, but we were able to fix that by changing the direction associated with our y values right there by introducing this negative. So we're on the right track is what I'd say so far. So we're on the right track. We still need to get the fact that we want to do 2 laps in 1 second. Well, what do I mean by this? Well, I know that 2 laps is the same thing as 4 pi, right? That's the same thing. And that needs to happen in 1 second. So that's saying for me, in the time interval from 0 to 1, I need to have traversed a full 2 pi. I'm noticing, and by the way, 2 pi or 4 pi, sorry, 4 pi is 2 laps, and that needs to happen in 1 second. So when I'm inputting t equals 1, I really need to be at 4 pi. Currently, when I input t equals 1, I am at 1 radian. I need to be at 4 pi times as much as that. And so what I'm going to do here is I'm going to then update my equation to represent this. I want there to be, I want to go 4 pi times faster than currently. And so I think I can update our equations then to x of t equals 2 cosine 4 pi t, y of t equals negative 2 sine of 4 pi t. So this is my guess right here for my final answer, and I want to go verify this now in Desmos. And then we'll look at one more problem and call it a day here. We haven't really done any math today. Our last problem will have a little bit of math in it here. So let's pop over to Desmos and see if this response is correct right here. So I'm going to go back over to my browser. I'm going to get rid of my other statements here. I am thinking that we are trying to graph cosine of 4 pi t negative sine of 4 pi t. It's giving me the circle, which twos go in here. So notice here, I'm at a radius of 2 as we expected right there. Very importantly, I do want exactly these bounds that it gave me. I do want to go from 0 to 1, and I'm seeing that this does in fact give me one full circle that we're traversing right here. Or is it giving me one full circle? Maybe it's not just one full circle, right? I kind of want to know, shouldn't that be 2 full circles? It's hard to tell when they're overlapped on top of each other. If there's 2 circles on top of each other, you can't tell. And that's why you have to put a particle also on your curves. So 2 cosine of 4 pi a, negative 2 sine 4 pi a, and I add my slider for a. Now, super importantly here, we decided that in 1 second, we want this stuff to be traversed. So if I'm checking out my a values here, it's critical for me that I set these specifically for the 0 to 1, and I better see 2 laps happen as I traverse 0 to 1. If that doesn't happen, then we did this wrong, right? So at time 0 is my first thing right here, and notice we are at the desired, we are at the desired starting location of 2, 0. It's where we wanted to start. So one good thing I'm seeing is in our earlier graphs, we were starting up top because we had sine then cosine. Now we have cosine then sine. It's moved us to 2, 0 instead of 0, 2 right there. We flipped those two things. So we're starting at 2. We want to go in the clockwise direction. Clocks would be going in this positive rotation direction, right? Or wait, talk myself out of things here. And so let's see if we get that. So as I increase my slider, I do see that we're going in the clockwise direction from 2, 0. And I do see that that we have made one full lap in half of a second. And now we're going to get another full lap. Right, so there we go, right there. 2 laps just happened in a lapse 1 second of time. My time interval went from 0 to 1. 2 total laps were traversed around the circle from 2, 0 in a clockwise direction. So notice that the big thing about parametric curves is not about the shape of the curve, but trying to craftily design things so that they have the appropriate starting locations, directions of motion, and speed of traversal. These are kind of really the bigger buggers for you to be able to work out here. And that's why it's really important that you do guessing things. It's really important that you play around with things in Desmos to verify your guesses or to just help change your guesses. Like maybe you couldn't remember what to do with the radius. Well, we could have left 2 out here and put this in as R, right? That could have just been an R right there. And then I can add a slider for R and say, oh, yep, it looks like just like I thought. If I make my radius 2, I get bound, or the R2, I get radii out to 2 if they're bigger, smaller, whatever. So like realize that like let playing around in Desmos be your friend right here. Guessing and checking for you today is literally 100 times easier than it was 30 years ago. 100 times easier. So even if you are annoyed by this, you should get over it because this is way, way, way easier than 99% of people who have ever learned this have all struggled more because they haven't had Desmos. You are right now at the peak of technological visualization that we've ever experienced in humanity, and therefore you have like a huge advantage over anybody else that has ever learned these things, specifically because Desmos exists. So be in there. Make this your best friend for investigation of graphical type things here. So let's pop over and look at one other question and we'll call it a day here. So the last thing I want to consider here is the difference between trajectories overlapping and a collision occurring. And we're going to check to see when we're going to experience overlaps versus collisions right here. So in our last example of the day, by the way, this is number 43 from our textbook right here, problem number 43. They say, first, are there any overlaps in the trajectories of these 2 particles? So I'm first of all going to say, I don't really know what's going on here, but let's kind of take an eyeball look at these 2 particles. Particle 1 only. I see a sine and a cosine, so I'm immediately thinking circles. But In a circle, I would have my r term be constant everywhere, and it doesn't look like that's the case. It looks like our x values are going to be as broad as -3 to 3, and our y values are only going to go from -2 to 2. So I am guessing here that this is going to be an ellipse that's going to be centered at the origin, that's going to have a little bit wider x span than it has y span. All right, I'm picturing something like that ellipse. Just drawing a real rough sketch right here. But I see my x values go from -3 to 3. My y values go from -2 to 2. When I see sines and cosines, I think circles. But it looks like this is just a circle where the radius is always changing a little bit. That's an ellipse. This guy, I feel similar things as circles here. But I'm noticing I've got these additive terms. But I really just feel like this just says really like, I don't know, cover up the -3 with your finger, cover up the +1 with your finger. This is really just cosine and sine to me. So that says this is purely a circle. It looks just like all of our x values are 3 values lower. All of our y values are 1 value bigger. So this should just be a shifted circle right here. It looks like these values, I know that cosine goes from -1 to 1, -3 is going to give me -4 to 2. Sine goes from -1 to 1. If you add 1 to all those, you're going to get 0 to 2. Those are the outputs possible from this y of t equation right here. So I'm sort of picturing that there is a circle centered at -3, 1. That's going to give us that span of x and y values that we're seeing right there. Right? Does that make sense? There's my -3, 1 is at the center. And the x values, therefore, go from -4 to -2. The y values go from 0 to 2. And there's my circle right there. So what I want to know is, do these trajectories overlap? From Desmos, or just from our pictures that we graphed right here. Let's go ahead and graph both these guys. I'm going to come over to Desmos. We've got two different setups we want to graph now. And by the way, in this instance right here, I'm only interested in do the curves hit each other. So I don't care to put points on these. I'm just going to graph just the t stuff. No a's with slider bars in this case right here. So what were our equations here? We had 3 sine t and 2 cos t, 3 sine t and 2 cos t. I at least want to get this thing going for a full 2 pi so I can see the whole thing. And here we go. Just like I guessed, we have an ellipse centered at the origin. It looks like it does go 3 to the left and 3 to the right. It does go 2 up and 2 down as controlled by the radius of the x stuff, radius of the y stuff. Our other curve of interest here was, come back over to Word, my x value is -3 plus cosine t. And my y value of interest here was 1 plus sine t. And again, it's giving me a little piece of something. I want to see the whole dang thing, so I'm going to give it the whole 2 pi. And what do you know? This looks kind of very similar to the pictures that I had just kind of both graphed in our image out there. So it does look like there are 2 points of intersection. That's basically the answer to my question. It looks like these curves intersect at 2 locations. Two intersections. Make sure I get my picture right here. Oh, it switches back over to Word. And in my picture right here, I have this guy just sitting right on it right here. Oh, isn't it smaller, by the way? No, it shares the exact same height as the ellipse. So those are the 2 locations of intersection. I can see them both right here. All right, 2 points of intersection. Now, watch a funny thing right here. Hopefully, you guys are all comfortable enough with Desmos to come over here and say, oh, where are they? And click on them. But I'm clicking, and it's not doing anything to me. Well, turns out Desmos has a bit of a struggle with finding those XY locations where the intersections occur when we define equations parametrically over here. So unfortunately for you, Desmos is not able to tell us where these points of intersection occur when we define these two different curves parametrically right here. It's a bit of a bummer right there. Right? I can see where one of them is. I can see that negative 3, 0 is a location of intersection, but that's still not super helpful for me. Here's the thing that I'm not sure about, though. The thing that we're unsure about in this case is, just because these trajectories intersect, does that ever mean that these particles collide? Or could it be that they're just doing something like this for all time, and both traveling in circles that technically overlap each other, but never actually hitting each other? Or are they going around and like dinking against each other every time? Here's two circles that should overlap, where the particles have to hit each other each time they go around. Or are they, two circles that overlap? Here we go. They're both on two overlapping circles, but they're never hitting each other in this visualization either. So just because two trajectories overlap does not necessarily mean we're ever going to experience a collision between the two particles. What circumstances would we experience a particle collision? Well, overlap is telling me that x1, y1 has got to be equal to x2, y2 at some time. On the other hand, collision says x1 at some, I don't know, t star, I'll call it t star special time, y1 at some special time, equals x2 at a special time, y2 at a special time. The whole point here being that an overlap says they're at the same location, but maybe at different times. A collision is when they're at the same location at the same time. So it's really that the x's, the y's, and the t all need to be the same. So let's see if we can find if there is a collision or not. We have two candidates for collision. And here we're saying T star is time of collision. It's the special time at which they collide with each other. So what I need to have happen here is I need my x information for my first point to match my x information for the second. I also need my y information for the first point to match the y information for the second. And I need that to be true at one common time. So I'm not going to pick different times. I'm just going to use one variable t. So I need to have these two x equations be equal to each other and for these two y equations to be equal to each other. And we can go ahead and solve. So let's kind of set that up. So 3 sine t equals negative 3 plus cos t. Sorry, forgot them already. 3 sine t, negative 3 plus cos t. All right. That's a bit of a bummer equation. I can't really helpfully solve that in any smart, intelligible way here. But let's see what our next equation brings us. Y1 of t. We also need our y values to match at that time. So what are our y equations? Our y equations were 2 cos t, 1 plus sine t. So I'm setting these two equal to each other. 2 cos t, 1 plus sine t. So I don't know. It's not directly obvious what to do here, and you'll see this for all parametric equation solving. It's always like, I don't know, can I find some pieces that match some other pieces? So I don't know. So I guess here's some things I'm picturing. And again, I did this earlier. I ran myself in some algebraic circles. I eventually found the answer that I was looking for. So what I'm going to try and do right now is not look at my notes, but see if I can just run in my circles again right here. My first instinct is to say two of these three terms have a three in them, so maybe we should group those and factor it out. So maybe I could say like cosine of t is 3 sine t plus t, or plus 3. Uh-oh. I'm not going to do my backspace in here. I'm just going to erase now. And that would tell me something like cosine of t, I don't know. Well, actually, this is kind of maybe good for me because notice over here I have some cosine stuff. Maybe I can just build an expression here just in terms of cosine. So let's do this. Let's, oh, it's not going to let me draw over that thing right there. Okay. So I'm going to take that and I'm going to take this guy right here also. And maybe let's say here, this is what cosine of t is equal to. So I'm going to do a substitution into y. This is going to give me 2 times 3 sine t plus 3 equals 1 plus sine t. Sub that into the y equations right there. So I've grabbed my cosine of t. Cosine of t should be the same as 3 sine t plus 3, so I plugged it in. And let's see if we can go ahead and solve now for this stuff here. Let's see here. I'm getting a 6 sine t plus 6 equals 1 plus sine t. So I'm going to subtract the sine t's over. I'm going to subtract the 6 over. And I'm getting 5 sine t equals negative 5. That means sine of t equals negative 1. And now we ask the question, what is the angle that you take the sine and get negative 1? And hopefully we're all picturing on our unit circle that we're hanging out at that location down there. It looks like for us, t is going to be 3 pi halves. So this is the time of collision. So we found the time of collision. What is the location of collision? We know that we had 2 candidates for the collision. There was 2 different places where this could have been the thing that was happening. We know that it's either this point that's on the axis right there, or it's this one point that's in space right there. And I don't know which of the 2 we actually just identified. I know when they collide. I don't know where they collide in our XY diagram. So I think it's also reasonable if we're talking about collisions, not just knowing when it happens. And by the way, notice there's only one time, so apparently only one of those locations is representative of a collision location and one is not. So where is it going to be? We'll just plug in the time of collision. And so here, I've got 2 different ways I can do this. Here, maybe I'm going to have my Desmos read off my equations for me here. And here I'll say x1, y1 equals 3 sine 3 pi halves 2. Just trying to get ramped up here. Just trying to finish this problem. And then we're done. 2 cosine 3 pi halves. And sine of 3 pi halves is negative 1. So it looks like we're getting negative 3. Cosine of 3 pi halves is 0. Notice I could have also done this with x2 and y2. Here we had negative 3 plus cosine of 3 pi halves and 1 plus sine of 3 pi halves. And I'm noticing again here, cosine of 3 pi halves is 0, so we get negative 3. 1 plus sine of 3 pi halves. Sine of 3 pi halves is negative 1. 1 and negative 1 is 0. So this is our confirmation. And I think we can finally say 2 overlaps in trajectory. But only one collision at xy equals -3, 0 at time equal to 3 pi halves, and I'll say here plus 2 pi k. When I say there's one collision, I guess in 0 to 2 pi. If we took another lap around, we'd hit again at the exact same place at a coterminal angle to the one that we already saw right there. All right. So talking about collisions versus overlaps is a good distinction to make. An overlap occurs when x's and y's are the same. A collision occurs when x and y are the same at the same time. And it looks like we only solved for one time at which that was true. If there was going to be 2 different collisions, we would have found 2 solutions to this, and we didn't. So the fact that I only found one time solution from 0 to 2 pi leads me to believe that there was only one time of collision for our 2 candidates that were out there. All right. So what do we do? That was just like an investigation. I'm not even worried about this right here. I'm just going to throw this up on the screen right here. The thing that I want to, again, just like shout at you guys before we wrap it up for the day here is, again, stop for a moment and like literally actually think about learning this stuff 50 years ago. My dad is like 70, my dad's 71. He got his degree in engineering, not chemical engineering, not electrical engineering, not architectural engineering. He got his degree in engineering from Marquette University in 1969, I think. And pocket calculators had just been invented, but they literally weren't even allowed to use them. The most advanced technology my dad was allowed to learn when he took calculus was a slide rule. Okay. Everything is different now because you can explore things graphically easily. And when I say easily, I mean insanely easily, meaning I don't care if you get stuck with Desmos for 15 minutes. We're talking about you saving dozens of hours of time hand sketching graphs so that you can understand what's happening here. Okay. Even if you bang your head against the wall trying to figure out with Desmos for 5 hours, you are still looking at a tiny fraction of the amount of time that people used to have to spend to be able to visualize these things here. So the thing that makes me laugh is if you go look at like the challenge problems at the end of this section, they're all a piece of cake. You just type them in exactly as they are into Desmos and drag some slider bars around and you know everything. This used to take people hours of work. It now takes you not only no effort, but also no time because we have technology to do this stuff for us. So I'm not going to do this one right here. Just go to Desmos right now. It will take you 2 minutes to answer the challenge problem from the section right here because you're going to throw it into Desmos. You're going to get slider bars for A, N, and B, and you're going to slide them around and you're going to say, oh, A controls this. I can easily see that. B controls this. I can easily see that. N is a little bit weirder, but I still think as long as you let N, with N, let's change this, by the way, as a positive whole number. I don't just mean positive, but also whole number values of N are going to be nice for you. And just look at it, and you'll be like, oh yeah, that was really easy. And think about how hard, do this problem just to imagine in your brain how hard it would be to answer this question if you didn't have technology. And then sit there and say to yourself, thank goodness I'm going to college in 2020 and not when Tony's dad went to college and had to do the same problem with a slide rule. That is my close for today. So tomorrow's video, we're going to look at all of these exact same types of equations, except now we're going to see how do we do things like apply calculus operations to parametric curves that might, and again, I want us to keep in mind, like we looked at some very nice parametric curves today, but I still think that like this should be what you think of when you picture a parametric curve. It is a really wobbly trajectory that doesn't follow any shapes that you recognize, that fails the vertical line test outrageously, that maybe even overlaps itself. And we still want to think to ourselves, how can we do things like think about derivatives and integrals in this context where we're not defining y as a function of x anymore? That's what we're going to talk about in tomorrow's video. So I hope you enjoy Desmos here for this week and for next week. And I will see you for calculus with parametric curves tomorrow. Have a good one.